So you want to get up to speed on general purpose reinforcement learning,
Right.
and you want to do it fast.
Absolutely.
Well, you've come to the right place.
Sounds good.
We're taking a deep dive
Okay.
into a research paper.
All right.
It's called Towards General Purpose Model-Free Reinforcement Learning.
Oh, interesting.
And let me tell you, it's got some big ideas.
Yeah, this paper tackles a challenge
Okay.
that's been kind of plaguing the field of AI for a while now.
We all dream of AI that can learn to solve any problem, right?
Right.
With like minimal hand-holding.
Yeah.
That's the promise of truly general purpose reinforcement learning.
And this paper is exploring a really interesting path to make that dream a reality.
Yeah.
You see, the problem is
Okay.
that most current RL algorithms are kind of like picky eaters.
Picky eaters.
They excel at solving specific types of problems,
Okay.
but they struggle when faced with something new.
This picky eater problem
Yeah.
is a major roadblock to truly general purpose AI. To understand why, let's delve into what the paper calls discrete versus continuous actions
Okay.
and vector versus pixel observations.
Gotcha.
Can you break that down for us?
Absolutely.
Okay.
Imagine a robot arm trying to grasp an object.
Okay.
If the arm can only make a limited set of predefined movements,
Okay.
like open hand or close hand,
Uh-huh.
those are discrete actions.
Okay.
But if it can move smoothly and adjust its grip with fine-grained control,
Okay.
we're talking about continuous actions.
So discrete is like a light switch, on or off,
Yeah,
and continuous is like a dimmer switch
that's right.
with a whole range of possibilities.
Exactly.
What about these observations?
Observations are how the AI perceives the world.
Okay.
A simple example is using a set of numbers
Okay.
to describe the position and velocity of that robot arm.
Okay.
That's a vector observation.
Right.
But what if the robot is using a camera to see the object it's trying to grab?
Ah.
Now we're dealing with pixel observations, which are much more complex to process.
So back to the picky eaters.
Yeah.
These specialized RL algorithms work well with one type of action or observation,
Yeah,
but they need tweaking to handle others.
precisely.
And that constant tuning makes them less adaptable,
Yes.
less useful
Yeah.
if we want an AI that can truly tackle
Yeah.
a wide range of real-world problems.
Right.
So we need a more general-purpose approach.
Agreed.
And this paper suggests a solution
Okay.
that's inspired by a different type of RL.
You're right. There has been some exciting progress lately with model-based RL methods
Mhm.
like Dreamer v3 and TDMPC2.
Okay.
These have shown impressive results on
Okay.
various benchmarks.
They're less picky eaters, so to speak.
You could say that.
But there's a catch, right?
There always is.
There's always a catch.
Well, while powerful, these model-based methods are computationally expensive and complex.
Yeah.
That makes them harder to use in real-world applications.
Like trying to run a supercomputer in your living room.
Exactly.
Not very practical.
Not at all.
So what's the solution? This is where MRQ comes in, right?
That's right. The research paper introduces this new algorithm
Okay.
called MRQ,
MRQ.
which stands for Model-Based Representations for Q-Learning.
Okay.
It's a clever hybrid
Okay.
that aims to get the best of both worlds.
Best of both worlds.
The adaptability of model-based learning
Okay.
with the efficiency of model-free approaches.
Okay. This is where it gets really interesting.
Yeah.
MRQ doesn't actually plan
Right.
like a traditional model-based algorithm.
No.
Instead,
Okay.
it uses model-based representations
Huh.
to guide its learning in a more efficient way.
Right. It's like equipping a picky eater with a super tasting ability
Uh-huh.
so they can quickly identify the most nutritious parts of any meal,
Okay.
even if they've never seen those foods before.
I love that analogy.
Thanks.
So MRQ learns a set of features,
Yeah.
these representations,
Right.
that help it understand the relationship between its actions
Yeah.
and the value it receives from the environment.
Exactly. It figures out which actions lead to better outcomes
Okay.
without explicitly modeling the entire world.
Right.
And that's what makes it so efficient.
Now I'm a visual learner,
Okay.
and thankfully the paper provides some helpful graphs.
Yeah.
Figure 1, in particular,
Right.
shows MRQ holding its own against other methods across different benchmarks.
Okay.
And it's doing this while using fewer parameters
Right.
and training faster.
That's an important point.
Right.
This means MRQ could potentially be much more practical
There-
for real-world applications
Yeah.
where computational resources are limited.
Yeah.
This is crucial because, as we said, current model-based approaches,
Uh-huh.
while impressive, are resource hogs.
Right.
Imagine trying to run a supercomputer
Yeah.
just to control a robot arm.
Right. Yeah.
MRQ offers a potential way around that.
Okay. So tell us about the specific benchmarks.
Okay.
I know there were 4, right?
Yes.
Okay.
They tested MRQ on GYM,
Okay.
EMC, with both proprioceptive and visual observations,
Okay.
and Atari.
Okay.
Remember, we're talking about a single algorithm handling diverse tasks,
All right.
from robot locomotion to playing video games.
Wow.
All with one set of hyperparameters.
That's incredible. It's like having a single multi-tool
Yeah.
that can handle any repair job you throw at it.
Right.
What were the results like?
The results show that MemRQ really shines in the continuous control benchmarks like
Right.
GYM and DMC.
Okay.
This is significant because it means the algorithm can handle both vector and image-based observations effectively.
So MRQ aced the robot arm tasks?
Yes.
And the ones where the AI had to interpret images from a camera?
It did.
Yeah.
Now, it's important to note
Okay.
that it wasn't the absolute top performer
Okay.
in every single benchmark,
Uh-huh.
but its consistency and efficiency were remarkable. And remember,
Yeah.
the goal here is general purpose learning.
Right.
We aren't necessarily trying to beat highly specialized algorithms in their own niche.
That makes sense.
Yeah.
The paper also mentions something called a design study.
Mm.
It sounds pretty technical.
Yeah, it's a common practice in research
Okay.
to understand how different choices within an algorithm
Yeah.
affect its performance.
Okay.
They tested variations of MRQ,
Mm.
tweaking things like the loss functions,
Okay.
the complexity of the model,
Okay.
and the time horizons it considers.
So what did they learn from this design study?
Well, one key insight was
Aye.
that simply increasing the model's complexity didn't improve performance.
Wait, so bigger isn't always better?
Not necessarily.
Right.
In the case of MRQ, it seems that keeping things simple
Uh-huh.
and focusing on learning that linear relationship
Okay.
between state action pairs and value is more effective.
So quality over quantity.
You could say that,
Any other surprises from the design study?
yes, they found that some tweaks that helped performance on the GYM benchmark
Okay.
actually hurt performance on the Atari benchmark.
Oh, wow.
This is a great example of why testing across multiple benchmarks is so important.
Because what works for a robot might not work for a video game AI.
Exactly.
Different problems, different approaches,
Yeah,
even in the realm of general purpose learning.
you got it.
Okay.
So while model-based RL shows promise,
Yeah.
its complexity poses a problem.
Yeah.
That's where MinRQ comes in.
Uh-huh.
And the design study results
Yeah.
lead us to a really thought-provoking question.
Hit me with it.
If MMRQ can achieve such strong performance
Okay.
without the complex planning components
Yeah.
found in other model-based methods,
Uh-huh.
does this suggest that the future of truly general-purpose RL might lie in developing powerful representations
Wow.
rather than sophisticated search techniques?
That is a big one.
It is.
Okay, let's take a moment to process all of this. All right, and then we'll dive into that question.
Sounds good.
So to recap, we have this algorithm MRQ,
Right.
and it's a bit of a hybrid, right?
Yeah.
It's using model-based techniques to learn,
Uh-huh.
but it's not doing any explicit planning,
Right.
which is kind of the hallmark of those model-based approaches.
That's right. It's more about finding those clever shortcuts to good decisions
Mm-hmm.
rather than like mapping out every possible scenario.
This is super interesting because it really challenges some assumptions about what we thought was necessary for general-purpose AI.
Yeah.
I mean, it seems intuitive that an AI that can plan ahead would be more successful, right?
Of course, planning has its strengths.
Yeah.
It's been incredibly effective in areas like game playing.
Okay.
Think chess or Go,
Uh-huh.
where you can simulate moves and anticipate your opponent's strategies.
That makes sense, but those are pretty structured environments.
Right.
What happens when you move into the real world with all its chaos and complexity?
That's exactly where the problem lies. Planning becomes computationally expensive very quickly,
Okay.
especially when you're dealing with complex real-world environments.
But the number of possibilities explodes.
Exactly.
It's like if you're a self-driving car.
Right.
You can't plan for every possible pedestrian or cyclist or squirrel.
Yeah,
That might dart into the road.
precisely. And that's where the power of representations comes in.
Okay.
If you can learn a set of features that capture the most important aspects of a situation,
Uh-huh.
you can make good decisions without having to map out every possible outcome.
So it's about finding those crucial bits of information
Right.
that allow you to generalize your knowledge to new situations.
Exactly.
Kind of like how we as humans learn, right?
That's a great analogy.
We don't plan out every step we take.
Right.
We rely on our understanding of the world to guide our actions.
And that's what makes MemRQ's results so intriguing.
Okay.
It suggests that maybe, just maybe, focusing on representations could unlock a whole new level of efficiency and adaptability in AI.
Okay. I'm getting hyped about the possibilities here.
Yeah.
But let's be realistic for a moment.
Okay.
There are always limitations to any new approach.
Right.
What are some things that MemRQ can't do yet?
Okay.
Or areas where it needs more research?
That's a great question, and the researchers themselves acknowledge that this is just a first step.
Okay.
One area where MemRQ might struggle is in tasks that require long-term planning or reasoning about complex sequences of events.
Because it's focused on making good decisions in the moment.
Right.
Not necessarily strategizing over a long period of time.
Another limitation is handling situations with sparse rewards.
Okay.
Meaning the AI only gets feedback on its performance very rarely.
That makes learning much harder.
It does.
Like trying to find a needle in a haystack when you only get told warmer or colder every 100 tries.
Exactly. And of course, there's always the question of how well these results will translate from simulated benchmarks to messy, unpredictable, real-world applications.
Because a robot arm in a simulated world doesn't have to deal with things like gravity or friction or, the cat deciding to sit on its work surface.
Exactly. So while these results are incredibly promising, there's still a lot of work to be done.
But that's what makes this field so exciting, right?
Absolutely.
There's so much we're still learning about how to make truly intelligent machines.
I agree. This research paper, along with algorithms like MRQ, are pushing the boundaries of what's possible.
We've talked about the problem, the limitations of current approaches, and a potential solution with this hybrid algorithm, MRQ.
Yeah.
What stood out to you the most in this research paper? What was your biggest aha moment?
What really fascinated me was how this research highlights the importance of understanding the why behind AI's success, not just celebrating that it works.
Instead of just focusing on the what,
we
need to dig deeper and understand the how and the why.
Exactly. It's easy to get caught up in the hype of new algorithms and impressive benchmark results.
Yeah.
But it's crucial to dig deeper and ask, what principles are driving this progress? What can we learn from these successes that can guide future research?
Because if we only focus on the what, we might miss out on the fundamental insights that lead to truly groundbreaking advancements.
I couldn't have said it better myself, and the researchers' design study was a perfect example of this. They didn't just test different variations of MRQ. They carefully analyzed how those changes affected its performance and drew valuable conclusions about the algorithm's inner workings.
Which led them to discover that simplicity in this case was actually a strength, not a weakness.
Precisely, and that's a lesson that applies far beyond this specific research paper. It's a reminder that as we strive for greater complexity in AI, we shouldn't underestimate the power of elegance and understanding the fundamentals.
This reminds me of something I read a while back about the power of Occam's razor.
Oh, yeah.
The idea that the simplest explanation is usually the best.
That's a great connection. And it speaks to the beauty of this research. It's not just about building more powerful AI, it's about understanding the principles of intelligence itself.
Well, on that note, I think we've covered a lot of ground today.
We have.
Let's take a quick break and then come back to wrap up our deep dive into general purpose reinforcement learning.
Sounds good.
Okay, I feel like we've been down the rabbit hole here. Exploring this idea of general purpose AI.
It is a fascinating topic.
What it means, how it works, and why it matters.
Absolutely. And it seems like this whole quest for general purpose RL is pushing us to rethink some fundamental assumptions about intelligence itself.
Yeah, for a long time, the dominant paradigm in AI was all about symbolic reasoning. Think rule-based systems that could manipulate symbols and logic.
Right, but those systems were very brittle. They couldn't handle uncertainty or adapt to new situations very well.
It's like trying to program a computer to understand humor.
Yeah.
You can give it all the rules about puns and irony,
Right.
but it's still going to miss the nuances.
Exactly.
And then along came machine learning.
Right.
Suddenly AI could learn from data,
Yeah.
recognize patterns, and make predictions.
It was a game changer.
It really was.
And reinforcement learning takes that a step further.
Okay.
By allowing AI to learn through interaction,
Uh-huh.
to experiment, to make mistakes, and to improve over time.
Which, as we talked about earlier, is much closer to how humans learn.
That's right.
We're constantly interacting with the world,
Yeah.
getting feedback and
Yeah.
adjusting our behavior.
Right. And that's why I think this research on MRQ is so exciting.
Okay.
It's not just about building more powerful algorithm. It's about understanding the core principles of learning and intelligence.
So let's bring this back to reality for a moment.
Okay.
What does all this mean for us non-AI experts? Why should we care about this research?
Well, for one thing, general-purpose AI has the potential to revolutionize countless industries.
Okay.
Imagine robots that can perform a wider range of tasks, personalized education systems that adapt to each student's learning style, or medical diagnoses that are more accurate and efficient.
Okay, those are some pretty compelling examples.
They are.
But are we talking about science fiction here?
Right.
Or is this something we might actually see in our lifetimes?
That's the million-dollar question, and honestly, no one knows for sure.
Yeah.
But I think what's important is that researchers are asking these big questions, pushing the boundaries, and exploring new approaches.
Like MinRQ.
Exactly.
This algorithm that's showing us that maybe, just maybe, there's a more efficient path to general-purpose AI.
Right.
One that focuses on the power of representations rather than brute force planning.
Exactly.
I'm ready for that future.
Me too.
All right, before we wrap up, I want to leave our listeners with a final thought-provoking question to ponder.
Okay.
We've talked about how MinRQ challenges the assumption that complex planning is essential for general-purpose AI.
Right.
So if representations are the key, what does that tell us about the nature of intelligence itself?
Oh.
Is it more about recognizing patterns and making connections than it is about meticulously planning out every step?
That is a great question, and one that philosophers and scientists have been grappling with for centuries.
Right.
But I think it's safe to say that intelligence is likely a multifaceted phenomenon.
Okay.
With both planning and pattern recognition playing important roles.
So MinRQ is giving us a glimpse into one possible piece of the puzzle.
Exactly. And as we continue to explore the world of reinforcement learning, we're bound to uncover even more fascinating insights into the nature of intelligence, both artificial and natural.
Well, that's all the time we have for today's deep dive into the world of general-purpose reinforcement learning.
It was great being here.
A huge thank you to our expert for sharing their knowledge and insights.
My pleasure.
And to you, dear listener, thank you for joining us on this journey of discovery.
Yes, thank you.
We hope you learned something new and exciting today.
Absolutely.
Don't forget to check out the show notes for links to the research paper and other resources.
Right.
And be sure to subscribe to The Deep Dive for more fascinating explorations
Yes.
into the world of cutting-edge science and technology.
I'll be here.
Until next time, stay curious.